Colligative properties, essentially the properties of solutions, that how a solution will change when we add solutes to it. And we looked at that chiefly around chapter 13, but the idea was that we could look at how three properties. We looked at vapor pressure, how that changed when we dissolve something. Then times the P star. We looked at freezing point. We looked at freezing point depression, which was delta TF. It was negative I KF M. We looked at boiling point elevation, positive I K B M. And we looked at osmotic pressure, which is pi I, NRT, MRT. So those are the key equations there. There's also one other thing which we could look at, Henry's law, which just real quick related solubility to pressure, that just the solubility is equal to a constant, Henry's constant, times a pressure. That's the easiest thing in the world. That's the easiest thing in the world. But to do these, we have to know a couple other types of concentration things. But let's start with the solubility. If it basically relates, if I have a constant that says KH is equal to 0.00323 moles per bar, and I say I have pressures 32 bars of whatever the gas is, to figure out the solubility is just going to be 0.00323 times 32. If, for example, I were to give you this in, like, I don't know, PSI or torr, you might have to convert. But it's practically just multiply those two numbers together. So your molarity in this case would be 0.10336 molar. Now, another way you could give it, if I said at 32 bar, this is the concentration, and then I say, what would be the concentration at 25 bar? All you'd be doing, you'd say S over P is equal to S over P. S1 over P1 equals S2 over P2. Because you're essentially just finding this constant and plugging it in again. This is kind of a weird equation, but really, if you're watching your units, of this constant, it's a really easy concept. But okay, so going back to these guys, we need to know M. We know M is just, remember, moles over liters. So that's easy. But X is mole fraction, which would be moles of whatever we're looking over total moles. And M, the molality, is moles of solute over kilograms of solvent. So this case, we are separating our moles. We're separating our solute from our solvent. So instead of liters of solution, it's mass of the solvent alone. Mass of the solvent alone. So let's try a couple quick questions with these guys. Now, I can't imagine we're having something this intense for the final, but hypothetically, we'll go ahead and kill two birds with one stone. So we'll say, we'll say 32 grams of methane and 10 grams of ethane. What is the vapor pressure of methane? Yeah, that's probably not a good choice because they're already gases. Let's say we'll do water and ethanol, C2H6O. What's the vapor pressure of water? At 25 degrees. The 25 degrees is just to throw us off. Say the vapor pressure, pure vapor pressure is, one thing we'll need to know is the pure vapor pressure. Pure vapor pressure is, we'll say 25, let's say, yeah, 25 torr, or I'm just making this number up. So the P star is 20, the P naught is 25 torr. So let's say the pure vapor pressure of water at 25 degrees. So the first thing we'd have to do is find out what is our mole fraction of solvent. So we're going to take our 32 grams of water, turn that into moles. Divided by 18. That's going to be 1.778 moles. Then we're going to take our 10 grams of ethanol and turn it into moles. 12 times 2 plus 6 plus 16. That's 46 grams per mole. So that'd be 0.217. So the mole fraction of water is going to be 1.78 divided by the sum of 1.78 plus 0.217. 8 divided by, and that'd be, the mole fraction is 0.89. 0.891. So plugging that in to our equation, 0.891 times 25 torr would be, the vapor pressure of water has dropped to 22.3 torr. It's dropped by a small fraction. But so to do the mole fraction, depending on what we want the mole fraction of, it's just moles on top over total moles on bottom. Not really hard of a concept. Maybe a little new, but not really that hard because it's just moles over mole, total moles. Now, freezing point depression and boiling point elevation are essentially the same beast. They're essentially the same beast in that, okay, freezing, let's say, for water is 1.86. In that it's the same equation, except you put in a different constant and a negative instead of a positive. So this is degrees C per molal. Now the I, remember our I in our equation, our I was how many ions does the solute break up into? How many ions does the solute break up into? So if, for example, it's a covalently bonded structure, it's not going to break up into any ions. The number is going to be 1. If it's something, a salt like sodium chloride, maybe it's going to break up into 2. If it's on like magnesium chloride, it's going to break up into 3. So we look at what are the ions? So if I dissolved in, I'm going to be pain. If I dissolved in 15 grams of ammonium chloride into 300 grams of water, what would my freezing point depression? Well, if I break this down into cation and anion, I is 2. Just because it's NH4 does not mean that's 5. NH4 is ammonium. It is a single ion. It breaks down into essentially 2. So our I is going to be 2. I've given you our Kf, so now we just have to find our molality. So molality is moles over kilograms, so we're going to turn the 15 grams into moles. The molar mass, 14 for nitrogen, 4 for the 4 hydrogens, and 35.45 for the chlorine. So 15 divided by 53.45, 0.28 moles. Now divided by kilograms of solvent. So 300 grams is equal to 0.3 kilograms. So 0.935 is our molality. So at this point, I, as I said, is 2. So we'd have negative 2 times 1.86 times 0.935. So that means our temperature would drop by negative 3.48. Now, if this was anything but water, then you might have to subtract that number from its freezing point. Because water's freezing point is 0, 0 minus 3.48 is negative 3.48. So we don't have to do any fancy math here. That's our answer. But for example, if this was a boiling point elevation, our new boiling point is 103.48. But we don't have to worry about that because we're not doing boiling. We're doing freezing. And vapor pressure, and not vapor pressure, but osmotic pressure is the pressure created when between two barriers when we have a difference in molarity on one side. So I could use the same situation. Ammonium chloride, 300 grams of water. The only problem is we'd have to figure out the molarity of the solution. We're going to make an assumption. We're going to assume that the solution is 300 mils. Oh, now that's maybe not the best assumption because as the ammonium chloride will take up some volume, so it should probably be 301, 302, 300, I don't know, 310. I don't know. I'm gonna just make our life a little bit easier for this. So if that's the case, if it's 300 mils, we would still have a 0.28 divided by 0.3 liters. So our molality is still the same. Now molarity is still the same. Now, to do the osmotic pressure is just our I, our M, and then RT, R being our gas constant, which is ATM liters per mole Kelvin. And if this is, we'll say this is at 298. We'll say this is at 25 degrees to make our lives a little bit easier. We just have to multiply those numbers together. So the pressure under this situation would be 45.7 ATM, which is pretty high, all things considered.